everyone. In this chapter, we are going to begin our study of fluid mechanics. At first, fluid motion can look complicated: water flowing through the pipes, air moving around the vehicles, or smoke swirling around an object. But the main goal of this course is to bring mathematical order to these physical systems. Fluid mechanics gives us a way to describe, predict, and eventually design systems involving liquids and gases. By the end of this chapter, we will not solve every complex problem, but we will build the basic language and classification tools needed to understand them. Fluid mechanics is the science that deals with how fluids behave either at rest or in motion. Here, the word fluid includes both liquids and gases. A simple example is a simple example is water flowing over a waterfall. The motion looks chaotic, but it follows physical laws. We can study the velocity, pressure, forces, and energy changes in that flow. Fluid mechanics also includes the interaction of fluids with solid boundaries. For example, water flowing through a pipe interacts with the pipe wall, and air flowing over a car interacts with the car surface. Sometimes the term fluid dynamics is used for fluids in motion, while fluid statics refer to fluids at rest. Fluid statics is really a special case where the velocity is zero. Fluid mechanics belongs under the broad field of mechanics. Mechanics is the branch of physical science that studies bodies at rest or in motion under the action of forces. Traditionally, mechanics is divided into statics and dynamics. Statics deals with the bodies at rest, while dynamics deals with bodies in motion. Fluid mechanics overlaps with both areas. A fluid can be at rest, like water stored in a tank, or it can be in motion, like air moving around a pipe or water flowing through a pipe. So, fluid mechanics includes both fluid statics and fluid dynamics. This is important because some basic principles, force balance, conservation of mass, conservation of momentum, conservation of energy, will appear throughout the course. And here in this slide, we will take a look into the no slip condition, which is a common terminology that you will hear across fluid simulations or fluid analysis whenever you encounter such type of problems. When a real fluid flows over a solid surface, the fluid directly touching the surface has the same velocity as the surface, which means if the wall is stationary, the fluid velocity right at the wall is also zero. In other way, the fluid layer which is adjacent to the wall will stick onto the wall and will not move along with the rest of the fluid. So that way, it is called no slip condition. This may sound like a small detail, but it has major consequences. Away from the wall, the fluid may be moving fast. At the wall, it is stopped. That means the velocity must change rapidly near the surface. The thin region where this velocity change occur is called boundary layer. Inside the boundary layer, viscous effects are very important. This is where friction, shear stress, and velocity gradients become significant. The no-slip condition leads to another important phenomenon called flow separation. When fluid flows over a curved surface, the boundary layer may not always stay attached to the surface. Under certain conditions, especially when the pressure increases in the direction of the flow, the fluid near the wall slows down and may eventually reverse direction. At that point, the flow separates from the surface. After separation, the flow becomes more complex, often forming vortices, wakes, and turbulence. This is why flow separation is important in engineering. It affects drag on vehicles, lift on wings, losses in pipes and ducts, and performance of turbo machinery. So the key idea is a simple wall condition can lead to very complex flow behavior. Now we will classify viscous and non-viscous, or otherwise called as inviscid regions. In many practical flows, we divide the flow into viscous and inviscid flow. Viscous flow refer to the regions where frictional effects are important. These effects are usually strongest near solid surfaces, especially inside the boundary layer. Inviscid flow refers to regions where viscous forces are very small compared to the pressure or inertial forces. This usually occurs away from solid boundaries. This does not mean fluid has no viscosity. Real fluids always have viscosity. But in some regions, the viscous effects are small enough that we can simplify the analysis. This is a common engineering strategy. Keep the important physics where it matters and simplify where the effect is negligible. Another small classification is internal versus external flow. Internal flow occurs when fluid is completely bounded by solid surfaces. For example, flow through a pipe or a duct is an internal flow. In internal flow, wall effects are very important because fluid is surrounded by boundaries. Open channel flow is a special case. Here, liquid flows in a partially filled channel and has a free surface. Examples include rivers, canals, and drainage channels. External flow occurs when a fluid flows over a body, such as air flowing over a car, a wing, a wire, or a cylinder. In this case, fluid is not fully confined by walls. This classification matters because internal and external flows are modeled and analyzed differently. Another classification is compressible and incompressible. Now, flows can be classified based upon whether the density changes significantly or not. In incompressible flow, the density remains nearly constant throughout the motion. Most liquid flows, such as water flow at ordinary conditions, are treated as incompressible. In compressible flow, the density changes significantly. This is common in high speed gas flows, such as air moving around rockets, jets, or spacecraft. A useful measure here is Mach number, which compares the flow speed to the speed of sound. When the Mach number is less than 1, the flow is subsonic. At Mach 1, the flow is sonic. Above Mach 1, it becomes supersonic. And at much higher Mach numbers, it is hypersonic. For many mechanical engineering problems involving liquids and low speed air, the incompressible assumption works very well. The other classification is laminar versus turbulent flow. Laminar flow is smooth and highly ordered. Fluid particles move in layers with very little mixing between the layers. This is common in high viscosity fluids or at low velocities. That's what you see on the first panel of this figure. The transitional flow is an intermediate state at which the flow will become unstable and switch between laminar and turbulent. Turbulent is highly disordered flow. It contains rapid velocity fluctuations, mixing, swirling. Most high-speed flows in engineering systems are turbulent. The distinction is extremely important because laminar and turbulent flows produce different pressure losses, heat transfer rates, drag forces, and mixing behavior. Now we will introduce some terminology used to describe how flow changes with time and space. A steady flow will not change with time at a fixed point. For example, if the velocity at one location remains constant as the time passes, the flow is steady at that point. An unsteady flow changes with respect to time. It is also called as transient flow. A transient flow is an unsteady flow that is actively developing, such as during startup or shutdown. Uniform flow means the fluid properties do not change with position over a specified region. Isotropic means there are no directional preferences. The properties are same in all directions. Periodic flow means in time around a mean value, the flow will repeat. Many rotating machines like pumps, compressors, and vibrating systems involve periodic behavior. Dimensional simplification. Real flows are usually three-dimensional, but sometimes we can simplify them. A flow is described as one-dimensional, two-dimensional, or three-dimensional depending on how many spatial directions the velocity significantly changes. For example, air flowing over most of the car body may be approximated as two-dimensional in some regions, but near the mirrors, wheels, sharp edges, and vortices, the flow becomes strongly three-dimensional. This is not about whether the object itself is three-dimensional, it is about how many directions are needed to describe the important changes in the flow field. A good engineer does not automatically use the most complicated model. Instead, we have to ask the question, what simplification can be used without losing the effect of physics and still can be used to solve the problem. Developing pipe flow. So this figure shows how the flow will evolve in a pipe over the period of time and over the location. At pipe entrance, the velocity profile is still developing, which means it is transitioning into a different profile because of the wall shear effect. The fluid near the wall slows down because of the no-slip condition, while the center region may still move faster. So when it was entering into the pipe, it had a rectangular type of profile as you see in the figure on the left side. And the length of the arrows corresponds to the magnitude of the velocities at those locations. And you can see the velocity gets reduced near to the wall, but it gets compensated and increased at the center. Further the downstream, the velocity profile becomes fully developed. At that point, the shape of the velocity profile no longer changes in the flow direction. The velocity mainly varies only across the pipe radius. So downstream, the problem becomes much simpler and often can be treated as one-dimensional in the flow direction with a fixed cross-sectional profile. Mathematical modeling pipeline. We begin with a physical problem, then we identify the important variables and make assumptions. For example, we may ask, is the flow steady or unsteady? Is it compressible? Is it one-dimensional or two-dimensional? Are viscous effects important? Those type of questions we will ask ourselves and will try to classify accordingly. And after that, we formulate the governing equation, often using conservation of mass, momentum, or energy. Then we apply boundary and initial conditions. These conditions connect the mathematics to the actual physical situation. Finally, we solve the problem and interpret the results. Now, a common question people ask is, differential equations, are they really necessary? Do we really need to study? Is it important in life or not? So this is one particular situation where differential equations become super useful, because use of differential equations makes the problem much more easy to solve, even though the mathematics looks difficult. Without using differential equations, solving the fluid dynamics problems will become a highly challenging task. Because naturally, the differential equations are useful because they describe how the physical quantities change from point to point or moment to moment. Or in mathematical terms, we can say the variation of one quantity with respect to spatial dimensions like x, y, z, or with respect to the time dimension dt. So with that type of link, it is easy to formulate differential equations for these type of problems, and then we can solve it. So that is the theme of this chapter, and I would encourage, do not just rely on these slides. You have to read the textbook also. There are things that I have omitted in this presentation, like units, then some other basic things which is self-explanatory if you read the textbook. So I encourage you to read the textbook as well, and see you in the class.